Disproportionation is when a particular element is able to both reduce and oxidize. And it happens to a few elements in particular oxidation states. So for example, in this first example, you've got copper 1, copper plus, that can both go to copper solid, undergo a reduction, and to copper 2 plus, therefore undergoing an oxidation. So we say that copper has disproportionated in these conditions. The next one is the example of, for example, of the ion manganate, and it can both oxidize to permanganate and reduce to manganese oxide. It is possible that some particular species are unstable with respect to this proportionation. I will be speaking up later on in another slide. When a species is unstable, so it's at risk of disproportionate, of both experimenting a reduction and an oxidation, you can stabilize by playing with their chemical and redox properties. For example, in the case of copper, you can either help avoid the reaction by precipitating copper 1 as copper chloride, or by complexating the copper 1 with a cyanide anion, in this case four molecules of cyanide. In the case of the manganate, the reaction is slowed down if instead of an acidic pH, the medium is a basic pH. So basic pHs will stabilize the manganate anion and will prevent disproportionation from happening. Potential diagrams, also called Latimer diagrams because of the chemists that came up with the idea, are a way of giving an overview of all the oxidation reduction processes that happen for a particular element at a particular pH. So for example, this is an example of the various species manganese can stabilize at pH 0 and the electropotentials in between those reactions. So in one, you have all this information of all these reduction processes. They're all written as reduction processes for manganese, for manganese at pH 0, and the same at another pH. In this case, pH 14. You've got the same, the same species and some additional ones that are stable at pH 14, and the different electropotentials, not standard in the case of pH 14, electropotentials for those reduction reactions. Another interesting type of diagrams used in redox chemistry is the Frost diagrams, or also called Frost-Epworth diagrams. And this was Frost's idea. He came with this. He published a paper in the mid-50s talking about describing these diagrams. They are pH dependent. So in this specific one is a Frost diagram for the manganese species at pH 0. And it's a way of representing the different oxidation states in the x-axis, and in the y-axis the electropotential of the cell. Each point in the graph represents a particular chemical species that that element stabilizes. And it can give you the relationship of the different species that, in this case, manganese stabilizes at pH 0. And it tells you the relative stability in thermodynamic terms of those species. How stable will they be with respect to reacting to produce one of the other species? These are thermodynamic diagrams. Remember, we're looking at electropotentials, free energy. It tells you how stable they are thermodynamically against a particular reduction process. It doesn't say anything about kinetic stability. So the process can be favorable thermodynamically, but very slow, and then it will not happen because kinetically it's very slow. Frost-Epworth diagrams do not cover that. It's only specific thermodynamical stability. How susceptible or not a particular element in a particular oxidation state is to transform to another oxidation state. And you can establish a relationship between points that are adjacent, comparing two species that are near each other. But you can also establish relationships between two species that are further apart in the diagram. So how do you use them to predict the stability of the species, in this case the manganese? Well, the lowest point in a Frost-Epworth diagram highlights the most stable oxidation state. So the lower you are in the diagram, the more stable that oxidation state will be, and the lowest point is the most stable oxidation states of all the possible states of that particular element. So for example, for the case of manganese, the most stable species for manganese is manganese 2+. When you look at two points in the graph, and I'm going to pick, for example, the ion manganate and the metal manganese, so these 2 points, the ion manganate and manganese, moving downwards in the plot means the process is thermodynamically favorable. So what this means is that manganese in this is much lower, is lower than the ion hydrogen manganate in the diagram. That means the process of going from hydrogen manganate to the ion manganese, to the metal manganese, will be favorable. At the top of the diagram, the top right hand side of the diagram, are the stronger oxidizing agents for that particular element. So in this case, for the manganese, these 2 species, the permanganate and the manganate anion, in this case hydrogen manganate, are the strongest oxidizing agents of all the manganese species, which we do know is true. So again, lowest oxidation point, so lowest point, most stable oxidation state. You can connect any 2 points in the graph, and that will tell you which one is the most stable one, which way the reaction will proceed thermodynamically. The one that is at the lower in the graph will be the most favorable. That will be the direction the reaction will happen. And top right hand corner of the diagram shows you the stronger oxidizing agents for that particular element. You can also calculate the electron potential for any pair in a Frost-Epworth diagram. And you do that by picking the gradient of the line that joins both, divided by the number of electrons exchanged in the process. So for example, what would be the process of, what would the electron potential for this reaction? Manganese 2+ plus 2 electrons to produce manganese metal. Well, I first need to identify where those 2 points are and join them, and in this case they are already joined with a line. Then I need to identify what's the gradient of the line. So the final point would be roughly minus 2.5, give or take. That's the y coordinate. The y coordinate for manganese is 0. And the number of electrons exchanged in this particular reaction is 2. So this is minus 1.25. So you can join any 2 points and calculate what would be the electron potential for a particular reaction by taking the gradient of the line that joins them divided by the number of electrons exchanged in the process. Another way you can use Frost-Epworth diagrams is to work out whether a particular species will be at risk of disproportionation, of reacting with itself to both reduce and oxidize. And for that, you need to look at the position of the peak of that particular species and the two adjacents. So, for example, if we look at the ion hydrogen manganate, and the two species next to them, manganese oxide and the permanganate anion, this species lies in a peak between two other species. That means that species, the hydrogen manganate, is susceptible to disproportionate. It will disproportionate, at least the process is thermodynamically favorable. It disproportionate in permanganate and manganese oxide. When the species falls in a well, in a deep, like for example here, manganese oxide in between the manganese 3 and the hydrogen manganate, that means the species is not susceptible to disproportionation. Thermodynamically, that species is stable. So remember, if the species falls in a peak, then it is susceptible to disproportionate, and it falls in a thermodynamic sink, then it will not be susceptible to disproportionate.